When technology had just begun turning digital, we were there, pushing the boundaries of system innovation, helping transform the most advanced and demanding technical industries, while enabling completely new ones that are now redefining the way we imagine the future. Unleash imagination. Turn great ideas into reality. With Cadence.
Hello, everybody. This is Kundan Chand. I'm the Power Integrity Engineer working for Meta Platforms. And I would like to present the PDN measurement to simulation correlation. This is the work which we did along with Cadence, security engineer Pankaj, and myself, and we had some help from Meta, from Brad Jacula and Nondo, doing the measurements on the boards and going through the various measurement methodology and different setups. And the final step was correlating our measurements with the 3D tools and the hybrid solvers in the industry. Then let me go to the next slide. So I'll start off with the motivation why we wanted to do this correlation, and then go over in brief regarding the measurement methodology which we followed and what were the pitfalls we observed. And then this measurement methodology and the setup will be a little bit different from for the different measurements we did. So it'll be kind of broken up into various slides. After that, we go over the PDN simulations methodology and what are the different knobs and settings we used for the hybrid solver as well as the 3D full wave solver, and go over the different best known methods we should be using for correlation. And then followed by the various correlation examples and plots, how good we are able to do the correlation and the best practices, and followed by the summary for this work, which we did. Okay, so the reason why we started this correlation effort was we were not quite sure if our measurement equipments and the lab probes and other things which we had were enough to be able to measure as low as few milliohms in the lab. We had kind of the high frequency equipments where we could do like hundreds of gigahertz or tens of gigahertz measurement, but not sure about PI, power integrity robustness for the measurement, and we wanted to check that and really be able to do accurate measurements. And we had a lot of simulations running, and we're able to create the models for our team on various test boards, but we never had a close the loop with measurements and correlating them to our simulation models. So to get a feel of how good our models are, this was important. So in terms of the correlation to the simulation, we kind of I can divide it into three categories, and that's how we started off with a bare board and did measurements on the bare board, like without anything soldered onto the board, and just correlate the power delivery network plane capacitance. You have the power plane, and you're just correlating the capacitance with your simulation tool. Next step, we went ahead and intentionally created a short on one of the capacitor pads so that we could measure the bare board inductance in the tens of megahertz or hundreds of megahertz range. And the reason we did that is because we wanted to assess our measurement capability to be able to measure those few picohenries or few tenths of picohenries accurately. So that was the second step. And the third was finally we closed the loop with the populated board, where we had the we had all the decoupling caps soldered onto the PDNs, but we did not have the SOCs or any chips on the soldered onto the board. So we were able to access the BGA pads, and we could probe easily access those pads and probe on them. Yeah, so these are kind of the three correlation items we'll focus on. So start with the measurement setup and the equipment. Some of the details are here. So we had kind of Keysight E5061B, which is kind of suited more for the power integrity measurements. It can measure from I believe as low as a few hertz to up to 3 gigahertz. And we had another option which is more suited for lower frequencies. It's the Omicron is the company name, and Bodhi 100 is the equipment, and it could measure up to 40 or 50 megahertz, and that's the max frequency it can go to. And we tried both of these equipments, and we used the small Pico probes to access those tiny pads on the board, or BGA pads or capacitor pads, and the probes were used in conjunction with both the Keysight as well as the Bodhi 100. So in terms of the measurement setup, we use log scale and with the 1661 data points. So the reason we did that is for PDN measurements, typically we are concerned about the lower frequency stuff, especially with the populated board. We want to see, and if you have a PMIC, you want to include the PMIC effects or the VRM effects, then it's really important to measure in the low frequency, have enough number of data points. So that's the reason we chose like a little bit higher data points, log scale. Then we use the two-port shunt through method to do the measurement, which is kind of the standard way, where we, since the PDN impedance is so small compared to the port impedance, the port reference impedance, so we kind of look at the S21 or the transmission coefficient information and convert it back into the impedance. And the frequency range we use was kind of go from 100 kilohertz up to 1 gigahertz. And as we go forward, you'll see for each of the different sets of measurement I discussed before, different frequencies tend to become important. So we'll go over that. And the measurements were taken at the board capacitor pad locations. If it's a bare board, we just probe the pads of the capacitor, and also we probe the BGA pin pairs. Yeah, we already discussed about the two-port method, and then next we'll show the different methods, how we did the calculation and the de-embedding which was applied for the measurements. So yeah, for the impedance calculation and de-embedding, so here is the impedance calculation method. If you look here, there are three curves. So one is our conventional two-port, which is our raw measurement data, where we get the S21, and then we are able to extract Z21 from it. And the blue is just using the math calculation, like approximation, where we just multiplied by 25 and times S21 gives us Z21. and then the pink or the magenta is going to be a little bit more accurate assumption. So as you can see, for the purposes of our measurement, typically in the frequency ranges of few hundred megahertz, few hundred megahertz, and starting from hundreds of kilohertz, it kind of did not matter which either of the three we used. So that's the purpose of this, is just showing like if you're interested up to a few hundred megahertz frequency range, in which for most of the board PDNs we are, then we can choose any of the methods. Now for the de-embedded versus unde-embedded, if we used to calibrate at the tip of the Pico probes for some of these measurements, and we tried the method where we only calibrated using the eCal up to the end of the cables and compared the results. And we in one case we also included the Pico probe parameters, parasitics information, and with and without adding the parasitics, it did not matter. So this is the curve just showing like if you add the port parasitics into the and de-embed it versus not, it kind of does not matter up to the frequencies of interest. So that's another finding we had. And then based on this, we started off with the bare board plane capacitance correlation. So if you go, I'll just go over the setup or the board which we use for that. So here, just showing you in red is our plane. So there is kind of on the board layers, if you look, top layer is kind of the VRM positions, right? And then on layer 7, you can see the plane from VRM going from right to left. That's how your plane is extending, and this is the SOC boundary. And then this is the bottom or the layer 14. You can see the capacitors at the back side of the SOC. So this was our bare board, and we kind of looked at we probed at a couple of locations just to be able to get the bare board plane capacitance. And next, we can just see the results. So if you see the magenta is kind of showing the simulated bare board plane capacitance using the Sigrity PowerSI solver, and green is sort of the measured plane capacitance. And you can sort of see the correlation. There is kind of like 15%, approximately 15% difference between the measured and the simulated. And we kind of still looking into the cross section and look at the dielectric parameters for the board to be trying to close the correlation gap across it. Right. So this was just for the bare board. We were able to be in the ballpark for the correlation. So next step was we moved to recall the board inductance measurement and correlation. So here, what we did is we kind of shorted the power ground pads on the bare board to be able to just see the inductance on the plane. So this is a little bit more detail. So we had like these capacitor pads with power. The lighter green one is your kind of the power pads, and the darker green sort of are the ground on both sides of the power. And we kind of put the 2 ports in this fashion at the same pad location, and so we kind of shorted one of these power and ground together on the board, and you could probe any of these cap pads using the 2 probes and look at the results. And we also tried to probe on the other side of the board where you had the power and ground BGAs, and again the same pads. The probes were were put on the same pad pair. Okay, so there's a little bit more detail on the measurement steps for this case, where we calibrated to the tip of the probe for the two-port calibration, and then we kind of made sure that our calibration is accurate, and we used a known PDN on the bare board, and we measured each of these caps, which I was showing on the previous slide, each of these caps using the two-port method, and also the SOC BGA pair. And let's look at the correlation for that. And once we were confident about the correlation on step 2, only then we decided to move to step 3, which is measuring the PDN with all the capacitors soldered. So this is just for this measurement, we did it on 2 different setups. So I'm just showing the first setup is the exact same board, just 2 different setups were used. As you can see how the probes are landing on these on the power and ground pads on the same location. Actually, this figure is not fully accurate. So both the probes were landing on the same pad pairs, and this is kind of the other measurement setup where we used same board, and we probed like you can see here on the back side on the capacitor power ground pads, and on the top on the BGA pairs. And in one of the cases we had used Bode 100, the other is Keysight E5061B. And also there were some differences in the cables being used on both the setup. So yeah, this is just showing you the results, comparing the two measurement and simulation. So yeah, actually I misspoke. So here on both measure 1 and measure 2 setup, we used the E5061B, but the cables were different for both the cases, and also the cal procedure was different. So this is highlighted in here. For the measured 1, we used the Pico test cables and plus calibration at the tip of the probes, whereas measured 2 is we use the Huber-Suner cable and plus ecal at the end of the cable. So we did not calibrate till the end of the probe tip. And as you can see, based on the measurement result, so around these frequency range, they were kind of correlating pretty well with each other. Over here, up to 10 megahertz, there was some difference in the result, and we kind of digged into the details and found that for the measured 1 setup, when we were calibrating, when we were setting up the frequency points in the sweep, we kind of missed the points in this frequency range. So that's the reason you can see there's just one measurement point at this location and another one at here. And if we went back and did the measurement with including more points in this frequency range, and kind of found that they were correlating. So it is just a good example of some measurement artifacts which we could observe, and I just wanted to highlight that here. One more thing to note in this figure is, if you look at the lower frequencies, we were not particularly interested for this measurement purposes below like 100 kilohertz or so. But if you're interested to measure below this frequency range, we have to probably use an isolation transformer or a choke in the path, so to be more accurate up to a few hertz of measurement if you want to do like a resistance measurement or very low frequency impedance measurement. So yeah, I just wanted to highlight that part. yeah, so we kind of had the similar measurement, and then next step we went ahead and did the ran compared it to our simulation models. So here I'm just showing the red dotted one is your measured data, whereas the magenta is comparing two different full wave solvers. And we can see a pretty decent correlation around this frequency range, which we are more interested in. Tens of megahertz to a few hundred megahertz. And yeah, over here it's the same plot, just showing a little bit different scale. And we also compared these different solvers and included the Cadence 3D clarity solver, as well as the hybrid solver PowerSI to compare the results. So the green is showing the measured impedance, and you can see the other tool solvers are kind of reasonably correlated to the measured result. One of the things I want to note here is like when we ran the simulation initially, PowerSI was reporting around 40% lower impedance compared to the measurement, and kind of we worked with the application engineer for Cadence, and they were able to give us a setting to improve the correlation for this particular scenario, and we were able to get decent correlation using PowerSI after that. And this is again extracted the inductance from the measurement for the board, and just showing the results. Again, green is measured, and then you have the other field solvers inductance numbers. So going towards just a summary for this particular case, we intentionally created a short on the board to measure the inductance, and we were able to measure the impedance within 20% of all the industry tools. And the differences could be due to like different tool solvers may have different ports being used, and the different port parasitics in the simulation were not removed or de-embedded. And also the reference impedance which we used in the simulation tools were a little bit different, so that could also result in some other differences. And also like I mentioned before, the board profiles or the board parameters can have some impact on this. And I already mentioned about the PowerSI initially underreported the inductance number, but was later fixed after doing some setting changes. So once we were reasonably confident about this correlation for the bare board plane inductance, we went ahead and measured the populated board with all the decoupling capacitors populated on the board. And let's look at the results for the fully populated test board. Okay, so this is just the measurement setup for that. Again, like I mentioned, we use these Pico probes, and this is showing the calibration substrate for the using one of our probe partners, and we use this to do the short open and load calibration through calibration. And this is the just showing the BGA probing on the BGA pads we did. And just giving an example of how the short calibration and how the real measurement looked like. So we always looked at the Smith chart, since it gives us an idea of both the magnitude and the phase. For the short, typically this is the response we got on port 1 and port 2. We're looking at the short, and the changing phase. And this is the kind of the real measurement. You can see, depending on what kind of measurement we are doing, we can have some resonances at certain frequencies. So just showing, displaying that. And on the right side, you're seeing the same thing on for dB or the magnitude only. So this gives us an like intuitive feeling before we are making any measurement of how the calibration looks like. And sometimes the probe position matters a lot, where we are sometimes the signal, only the signal probe is touching the pad and not the ground, and vice versa. So we had to kind of do a little bit of work to rotate the probe and make sure both the both the signal and ground pins are touching the dot at the same time, so that we have no errors in the measurement. And this definitely looking at the Smith chart and adjusting the probes helped us to achieve that. This is just an overview of the plane, like the board PDN. So if you look here, just showing different PDN, where you have the PDN starting from the bottom and then going through our to our SoC, and you have these bunch of decoupling caps. These are kind of 3-terminal caps which are used on the board. And just on top of this area, you can see the DUT or our SoC sitting here, and the BGA pins for the this particular rail is being highlighted. And we probed like these BGA pins here, and also we probed some of the capacitor locations over here. So so for this case, especially this rail, if you look at the measured result in green and the simulated in blue, for our purposes, we are interested more in on this region, like tens to hundreds of megahertz region, where we if you look at the correlation data, we are seeing you know, like 4 or 5 milliohm difference between the PowerSI simulation data versus the measurement. And it's pretty decent correlation for our purposes in this region, and even the capacitance portion is looking reasonable. There is some difference in the series resonance area, like a 1 milliohm difference. So that we could attribute to some of the details, how we are doing the simulation versus we use the vendor S2P models, the capacitor vendor S2P models, to be able to try to do the correlation. So there could be some differences on that. At the later end of the presentation, I would be discussing more information on that. But overall, for the purposes of where we are interested, the measured impedance was within the 15% window of the simulation result. So here, this is again just showing the zoomed in, and we included the 3D solver Clarity, the Cadence Clarity tool, as well in the simulation. And this is measured at one of the capacitor pads. So as you can see, the Clarity tool is kind of related, kind of correlated to the measurement pretty well, and the PowerSI is slightly underreporting the result, but both are within that 15% window for here. Then this is just an example of a second PDN, where we had like some feed through X2Y cap being used, and they were They were also measured at the BGA pads, and just showing you both the waveforms are just slightly different scale again. And we, for the purposes of our analysis, we were interested more in the frequency ranges here, like tens to hundreds of megahertz. And again, this you can see around 6 to 7 milliohm difference. And I just want to mention for PowerSI, we use like the settings I'll be sharing in the later end of the presentation, what we use. So, but typically this is within that 15% of correlation range. Yeah, this is another PDN and measured on a separate board, a second board, where we again measured at the BGA pads, and if we look at the results, it's kind of correlating pretty well over here. Yeah, I just want to give what are the settings we use for the Security PowerSI. Yes, first of all, there is a special void setting in PowerSI where we depending on what value we provide, the tool goes in and either fills those voids fully, or they can leave it open. So for our purposes, we kind of did the automatic setting of those special void setting, because that's what mentioned by the application engineer. They wanted to for better accuracy. And the second step was, even though we were interested in only these one particular PDN rail, we still kept all the shapes enabled to include, any of the impacts on the field impacts happening due to other floating planes, etc. Right. So we kept that enabled, and then for these purposes, we kept our DC point disabled because we were only interested in tens to hundreds of megahertz range. So we did not include the DC point. And for the mesh, as you can see here, that we unchecked this option. We did not want to simplify the geometry, just run as is. And the port reference impedance we used was 10 ohm. Yeah, we could use like 100 milliohm or so, but we just stick to this. I think that was also suggested by the AE. And then these were some of the other options I just mentioned. We use adaptive sweeping mode, and we enable these options, coupling between field domains and coplanar trace coupling. Yeah, so overall, these were the settings we used. And then for Clarity 3D solver, we used the settings here, where the tool was much better correlated to our measurements in this case. So these are some of the theory we are still looking at, why we were seeing some of these correlation differences, especially around those series resonance frequency of the capacitor, and also in the tens to 100 megahertz range. So one thing from the PowerSI or solver point of view, it's possible that we were not able to model the below the copper skin cutoff frequency, whether the conductors were meshed or not. So that could relate to some inaccuracies below this skin effect cutoff frequency. That could be one of the reasons. The other was since we are using the vendor, the capacitor vendor S2P models in our in PowerSI, and the tool is extracting the PCB connection of these capacitors. but the coupling between the capacitor body or the capacitor S parameter and the PCB may not be captured by PowerSI tool. So that could also be related to some of the differences. Yeah, one of the other things it's not mentioned, but I want to point out is we did measure the individual capacitors from using in our lab, and found that compared to the vendor S2P models, the capacitance portion was well correlated, but the inductance or the ESL of these caps was not the same as the vendor S2P model suggested. So that could also be causing some differences in our correlation results. Yeah, so overall, just a summary, we did the PDN measurement across multiple boards for both bare board capacitance, bare board inductance, as well as on the populated board, the decap populated board. So overall, we were able to correlate within 15% of the simulation results. And we tried different solvers, including hybrid solver as well as 3D solvers from different tool vendors. Also, one of the findings we had is sometimes like a hybrid solver, example, PowerSI, can run into certain limitations for corner cases. So far, what we have seen, especially the corner case we created here, was we intentionally shorted a bare board capacitor pad, which we don't expect to encounter much in real scenario, but that can break some of the assumptions in the existing hybrid solver. And yeah, it was improved after we had a special settings, right? But that's something to watch out for. So one of the recommendation which we got from this was, in the initial sign-off phase, definitely we can use the hybrid solvers for our initial, just a quick check of how the PDNs are designed compared to spec. But for a final sign-off just before your board or your product is taping out, ensure that we are using a 3D full wave solver to cross-check our results. Yeah, here are some of the correlation learnings which I wanted to list down. Was yeah, first of all, in your simulation model, just make sure that all the vias, drill diameter, plating, your antipad dimensions are accurately included in the tools which we're using. Of course, all the PCB plane thickness and as well matters, especially from the fab vendor, or even better if you can do the cross section of the PCB. Use enough number of points in simulation. We already saw less number of points can cause some artifacts in the measurement, and always use a log sweep to enable better lower frequency PDN measurement. For the VNA, always using IF bandwidth of 100 Hz. We found this was improving our simulation results quite a bit, because if we used a higher IF bandwidth, we did see a lot of noise in our measurement results. Even though using the IF bandwidth of 100 Hz will result in a pretty slow calibration and measurement, but we still highly recommend doing that. Also, like I said before, we tried different cables, both Pico test cables we had, as well as the Huber-Suner cables with the VNA, and both were kind of give us similar result, at least up to gigahertz. However, we still recommend to use Huber-Suner cables if you don't require any bending of the cables to access your duct. So I already mentioned number 5, like we tried the ecal up to the end of the cables versus the calibration up to the tip of the probe. We're using short open load through calibration, but there was not much difference, at least for the frequencies we were interested in. So you could be using any of these methods and just make sure that the frequencies which you're looking for are not too high. And finally, we realize always using Smith chart to include both magnitude and phase helped us to position the probe properly before even starting the measurement, and so that both signal and ground pins of the probe are touching the dot at the same time. So these are some of the learnings which helped us starting out with our measurements and helped to do the correlation. Yeah, so I think that was the last slide I had, and I would like to thank Pankaj Ahirwar from Cadence and Brad Jacula and Nando from our group helping with this correlation method. Okay, yeah, thank you, and feel free if you have any questions.